Hi, welcome to one of Mr. Askey's AP Physics C help videos. I'm Kenneth McCann, and today I will be teaching you a little bit about transitioning from linear motion to rotational motion. So basically this is the same stuff you've been hearing for almost a year and a half, only instead of x and x naught and x final, you have theta naught and theta final. And instead of a plane, you have a circle. And it's a different way of thinking, but you're prepared for this. So first, you're going to measure everything in radians, and you need to learn what a radian is. Radian is represented as degrees, as beta, not degrees, never mind. Theta is the distance you travel along the outside of the circle divided by the radius of the circle. And then you see theta in the middle. And this works for angular velocity, which is omega, and angular acceleration, which is alpha. Only instead of s here, when you're finding omega, you put velocity, and instead of a here you have, instead of s here, you have a, acceleration, to find alpha. And then radian is, there are two radians in a circle, so you'll want to know that. And yeah, you can see that delta x is now theta, velocity is now omega, and acceleration is now alpha. And then omega is theta divided by time, alpha is omega divided by time, and you can see these on little circles. There's theta over time, which is omega, and omega over time, which is alpha. And these are the same kinematic equations that you've seen almost for a year. Basically same as orange, although with omega, alpha, and theta. So first black equation is omega final equals omega naught plus alpha times time. Second black is delta theta equals omega naught times time plus 1/2 alpha times squared. And finally, the third black is omega final squared equals omega naught squared plus 2 alpha delta theta. And these are all for trio situations, just like the orange equations. You need to have alpha as a constant, otherwise they won't work. Just like the orange equations, where acceleration must be constant, your alpha must be constant. And yeah, you're going to want to use these for all kinematic calculations with rotation. And here is a bridge equation for going from linear motion to circular. At your tangential velocity, which is going around the outside, is of course change in position over change in time. And this brings up something interesting. There are two forms of radial motion. There are two forms of motion when you're dealing with circles. The first one is, didn't mean to do that, sorry. First one is your tangential, which is you're going around the outside, just like you would if you're driving a car around a circle. You go around the outside. And that is entirely separate from omega, your angular velocity, which refers to your change in theta. It's your angle of the inside of the circle. So two completely different things, although they are related. You'll see that coming up in a little bit. And also two forms of acceleration. There's centripetal acceleration, which you probably saw in chapter 4, where your velocity squared, tangential velocity, of course, divided by your radius. And your angular acceleration is, of course, alpha equal. And then if you want to express your centripetal acceleration in terms of your radius and your omega, You plug them into your v squared over r equation, like this, and then you get your centripetal acceleration equals radius times omega squared. And you'll see these on some of ASCII's things, plus the AP test. Radians are referred to as S, which stands for seconds, and radians per second, or omega, is inverse seconds, or S to the negative first power. And then radians per second squared is also alpha, is inverse seconds squared, or S to the negative 2 power. So, now knowing all this, let's go work some problems. Okay, now to work those problems. Now, unless ASCII changed your notebooks to where you don't have these problems in them, don't worry. These were just in the notebooks a few years ago. At least in this case, these are problem 1. This is problem 1, problem 2, and problem 3 from the class notes. He should have something similar to these. So the first problem is a wheel rotating with the angular acceleration of 3.5 radians per second squared. Its angular speed is 2 radians per second at t equals 0. The question is, what angle does the wheel rotate through in 2 seconds? So if you start out with the second Black equation, delta theta equals omega t plus 1/2 alpha t squared. And plug in numbers. Delta theta equals 2 radians per second times 2 seconds plus 1/2 parentheses 3.5 seconds inverse seconds squared times 2 seconds squared. Remember to square that, the last seconds. And if you plug it all through your calculator, you should get change in theta is 11 radians. Pretty simple. And then it'll ask you to calculate the angular speed, and you start out with the first Black equation. Omega final equals omega naught plus alpha t. Plug in numbers. Omega final equals 2 inverse seconds plus 3.5 inverse seconds squared times 2 seconds. And omega final is 9 radians per second. So pretty simple. A lot like orange equations, but circular. Now, second problem is an electric motor rotates a grinding wheel at 100 revolutions per minute is switched off, assuming constant negative angular acceleration of 2 radians per second squared. How long does it take the wheel to stop? Now, didn't put this on here, but if you divide 100 revolutions per minute by 60 seconds, so 100 1 minute, and there are 60 seconds in a minute. Basically divide 100 by 60 and you get about 1.666 revolutions per second. And of course, plug that into your first Black equation, and your omega final equals omega naught plus alpha t. Isolate the time, so omega final minus omega naught divided by alpha equals t. Plug in the numbers. This would be 0 minus 1.66. Because remember, we're staying in seconds, not minutes. Then divided by 2 radians per second squared, and then you get your time as 0.833. Sorry. And then to calculate how many radians it turned, it's basically the same as calculating how far it went if you were in linear mode, but now we're in circular. You use the second Black equation. Delta theta equals omega naught times time plus 1/2 omega alpha t squared. Plug in your numbers. Delta theta equals 2 inverse seconds times 8.33 seconds plus 1/2 negative 2 seconds squared. And remember the negative since it's slowing down. And times 0.833 seconds squared. And your change in theta should be 0.97 radians. Now, the third problem is finding the angular speed of a CD in revolutions per minute when information is being read from the inner track, which in this handy little picture, this right here is the inner track, and this right here is the outer track. And the drive starts reading information from here, and it goes around in a big spiral until it goes to the outside. So of course, the angular velocity is different at all these points because the radius is different. So first, the way you want to approach this is you want to start with the innermost track radius of 23 millimeters or 0.023 meters if you want to convert it, and use an angular speed of 1.3 meters per a linear speed of 1.3 meters per second. So start out with the bridge equation. Tangential velocity equals radius times omega. Isolate omega. Since you know tangential velocity and radius, plug in your numbers, and you get initial omega as 56.52 inverse seconds. Now you do the same thing to the outside edge, although you plug in 58 millimeters instead of 23. And of course convert it into meters, 0.058 meters. Use your bridge equation, isolate omega, plug in your numbers, and scroll, you should get omega as 22.41 inverse seconds. So this has been a help video on how to transition to rotational motion, and I